So in this video, we're going to talk about stoichiometry. If you've been in class, you were introduced to the idea that basically stoichiometry is a fancy word that basically means we're looking at the relative amounts, the quantity of reactants and products and their relationship numerically to each other. If you haven't already read section 12.1, I highly recommend that you do, and if you don't understand something when you read it, that you would ask for some help or guidance if you don't understand something. So like I said, stoichiometry, officially defined, is a study of the quantitative or measurable relationships that exist in chemical formulas and reactions. So we're trying to measure how much product or reactant is needed in particular reactions that help us as a society or happen in general. The word itself comes from the Greek. Stoichion means element, metron meaning measure. That's where stoichiometry comes from. We're literally talking about measuring elements and their relative amounts to each other, which has everything to do with balancing. So again, it allows you to calculate the amount of products from a given amount of reactants and or how many reactants you need to produce a specific amount of product. This is no different from recipes. If you have random ingredients in the cupboard and you have some friends coming over all of a sudden, you can look at what you have and judge how much you can make, how much product you can make based on your reactants or ingredients you have in the cupboard. And vice versa, you might have a party that's planned and you know how many people are going to be there, so therefore you'd have to know how much food you would need, how much product you would need, and then you could calculate or figure out how much reactant or ingredients you need to buy to make sure you have the proper amount of product or food to eat. So it's very similar to what we use when we talk about baking or cooking and recipes. So some practical applications that we commonly see have to do with the nutritional value in food. Those numbers that you see on the sides of food, the nutritional content is determined by stoichiometry or something related to it. It measures pollutants in the air and again predicts costs of reactants based on the number of products. So how much is it going to cost you to have that party knowing the number of products? So to make this idea even stronger related to what we know in terms of baking or cooking, we're going to use a reaction that involves cooking or baking, and that is with Jiffy cakes. If you don't know, Jiffy cakes are just a brand of cake that you can make. You can get it at any grocery store. Jiffy's a brand. There's Jiffy waffles and pancakes and muffins and all kinds of things. They come in a blue and white box. This is not Jif peanut butter. This is Jiffy cakes. So the reaction for a Jiffy cakes is pretty simple. So again, this is an everyday analogy of stoichiometry with Jiffy cakes. Unfortunately, we will not work with Jiffy cakes throughout the entire chapter, but we can always look back on this and understand the basic concepts that will hold true whether or not we're talking about things like recipes or chemical equations. So Jiffy cakes require 1 box of Jiffy mix. That's what comes in the box. You'd have to add 2 eggs, not in the box, and 1 cup of milk. And that would produce, after some baking, so add some heat, you get 1 Jiffy cake. And just to make this a little bit easier as we work with these, we'll give them some symbols. We'll call this J, M, we'll call this big E, we'll call this C, M, and we'll call this big J little c. So different elemental symbols that represent these made-up elemental ingredients and product. So I'm going to give you some scenarios to talk about the concepts that we'll go over in the chapter related to Jiffy cakes. So one thing that we're going to assume, or I can tell you will happen in a given question, if the amount of ingredients or products are not mentioned, specifically the ingredients or reactants, it's assumed that you have an unlimited supply of those things. So for example, in number 1, I have 2 scenarios. They're asking us for how many Jiffy cakes are produced. Given scenario A, you have 15 eggs, and scenario B, you have 12 cups of milk. So we can work through both of these using dimensional analysis, a skill we picked up back in chapter 10 and first trimester, or second trimester, first half of chemistry, and realize that in either question, A or B, like any question we've come across, you start with a number. And for A, that number is 15 eggs. And I want to figure out in the long run, mapping this out, some number, how many Jiffy Cakes. And so again, getting fancy and using the symbol, Jiffy Cakes, would go right there. So using dimensional analysis, and this is the important thing. I know that many of you are gifted enough to see the ratio and the reaction, or the ingredients here, the recipe, if you will, what it takes and what the answer will be. But I want you to focus on being able to understand how to cancel off units and thereby set up the math to appropriately get the answer. So I'm going to multiply this by a conversion factor. Remember, conversion factors are equalities. The top and the bottom units are different, but they equal the same amount, or they have some kind of equality relationship. In this case, since I started with eggs, I don't want eggs anymore. That goes on bottom. Notice I'm just writing units, and in this case I want to get to Jiffy Cakes. I can see from my reaction that there's a ratio from the balanced coefficients that allow me to change from one substance to another substance, in this case eggs to Jiffy Cakes. So if I look at the reaction, there are 2 eggs for 1 Jiffy Cake. So that sets up not only the correct unit, Jiffy Cakes is left over because eggs got canceled out, but it tells me that mathematically, as you probably already did in your head, it's 15 divided by 2, which is 7.5 Jiffy Cakes. In scenario B, I'm going to write this over here because I'm going to run out of room. I have 12 cups of milk, C little m. Again, that's short for cups of milk up here. And same idea, can you set up the appropriate units to cancel them out to get what you want? I want to get rid of cups of milk. I want to get to Jiffy Cakes. If I look at my reaction, in front of CM, or cups of milk, is a 1. In front of Jiffy Cakes, there's a 1. That tells me the relative amounts, that's what stoichiometry is, of each product or reactant, and how to change from one to the other. Cups of milk goes away, and again, mathematically, it's not difficult. You have 12 Jiffy Cakes. All right? So for each scenario, scenario A and B, I have a different number of Jiffy Cakes, 7.5 in the case of 15 eggs, and for question B, 12 cups of milk, I have 12 Jiffy Cakes. Now, in reality, you're going to have all of these ingredients, including the Jiffy mix, involved here, and you won't have an unlimited supply. And again, just to point out, in case you missed it, for both A and B, I was assuming that you cannot run out of Jiffy mix. It is assumed that they are in excess, unlimited amount. So I might ask you things later on in the chapter, once we start converting between different chemicals and stuff. What's limiting my reaction overall? In other words, what is the limiting reactant? Which ingredient will I run out of first? And so this is easier to see if I put A and B, the scenarios A and B above, together. So if I look at it, if I have 15 eggs, 12 cups of milk, and unlimited Jiffy mix, what am I going to run out of first? Obviously not the Jiffy mix. It's got to be either the eggs or the cups of milk. There's a couple ways I can do this. I can look at the ratio between eggs and cups of milk, and I see that I need twice as many eggs as cups of milk. And looking at my numbers, 15 eggs and 12 cups of milk, this is not 2 times as many cups of milk. So I'm going to run out of eggs first. The other way you can look at this is you converted both eggs and cups of milk to Jiffy Cakes. And you had 7.5 Jiffy Cakes from the eggs and 12 Jiffy Cakes from the cups of milk. The smaller number of product, in this case the 7.5 Jiffy Cakes, will always point to what limits your reaction. So in this case, we would say the limiting reactant in the A-B scenario is eggs. And then what I might ask you also is, well, how much can you actually produce? If you have 15 eggs and 12 cups of milk, and eggs limit your reaction, how many eggs or Jiffy Cakes can you actually make? And that would be 7.5. I will never get to 12 Jiffy Cakes because I will run out of eggs before I get there. Now we could talk about, well, what's in excess? Well, it's obvious that the Jiffy mix is in excess, but the other limited reactant that I had was cups of milk, so we'd say cups of milk overall. All right, let's change over and talk about chemicals now. So all the stuff we just talked about with Jiffy mix is going to apply here. The only difference is now I'm dealing with a chemical equation rather than a recipe. So now I have a word or a sentence talking about a reaction. I have to translate that to a balanced chemical equation. So it's an ammonium nitrate. Ammonium is NH4. Use your ion sheet if you're not sure. Nitrate is NO3. This is ionic. Both are ions. This is +1. This is -1. Drop and swap. They stay the same. It decomposes to form dinitrogen monoxide and water. If I balance this, the ends are good. There's 2 ends there, 2 ends there. H's, there's 4 here, only 2 here, so I put a 2 there. The N's were good. O's are now at 3, so it's 1, 1, 2. So one of the important concepts, if you look at your I can statements, is can you look at a reaction like this and understand what those coefficients mean? You've hopefully had some experience understanding that these coefficients represent particles, so I could say that one formula unit of ammonium nitrate decomposes to form 1 molecule of dinitrogen monoxide and 2 molecules of water. So that's what happens on the particle level, how many particles are needed for this reaction to actually occur in real life. When we see reactions happen, this is happening many times over, but fundamentally this is the number of particles involved at the very least, or most. We can also look at the coefficients as, so we got particles, the coefficients are particles. The coefficients also represent, so equal particles, they also represent liters. And the last thing they represent are moles. And if you remember, on our mole roadmap, the only road that required a different number for our conversion for each substance was mass to mole. Because each substance, or most substances, have different molar masses, therefore they're thought of as in different amounts, or they have different size atoms. The only ones we can think of on the same playing field are particles, liters, and moles, because when we went to Particleville, it was always 6.02 times 1023rd. When we went to Volumeville, the liters were always 22.4. So another way I can think of this and write this out, your I can statements, number 1 in particular, was 1 mole of ammonium nitrate produces 1 mole of dinitrogen monoxide and 2 moles of water. With that in mind, this corresponds to what we said about the Jiffy cakes. Those coefficients basically tell you the relative amounts of stoichiometry between each of the reactants and products in the reaction. And therefore, we can do something new. We can switch between substances. Back in chapter 10, we switched units, but we never switched substances. This new idea allows us to do that. So I can convert from one substance to any other substance. It doesn't matter if it's a reactant to a reactant, product to another product. I can go backwards from product to reactant, or vice versa. It does not matter. I can go from one thing to any other thing. So let's look at how you would set that up with this equation. So here's a question about my reaction that we just wrote. How many moles of each product is produced from 2.25 moles of ammonium nitrate? So notice it says each product. I have 2 of them, so I should have 2 answers. And the first one, so I'll call this is product 1, this is product 2. This is because this is first and this is second as we read things. Notice we're going to start with my number. Always start with your number, 2.25 moles of NH4NO3. And again, I want to point out that the math and the relationship of the ratios is pretty simple if you're looking at this and understanding in general what we're talking about. So don't get caught up in the math because it's pretty easy and it might be too boring for you, but see if you can write the correct dimensional analysis to get the correct number. So I'm going to multiply this by a conversion factor, no different from what we did with the Jiffy cakes and the reaction we saw a second ago. The difference being only, I guess, that you're dealing with chemicals now. I don't want moles of NH4NO3 anymore. And I'm going to get the product number 1 first. And again, product number 1, I just arbitrarily, randomly picked this one because it was first here, is N2O. So I want moles of N2O. And again, it's asking me how many moles. And this is something new. This right here, this is my molar ratio. That's what I call a molar ratio. That's this thing right here. And I can make a molar ratio. I can change from eggs to Jiffy cakes. I can change from ammonium nitrate to dinitrogen monoxide by looking at the coefficients in the reaction. Ammonium nitrate is right here in the reaction. It has a 1 in front of it, so I write a 1 there. Dinitrogen monoxide is right here. It has a 1 in front of it. It's a 1-to-1 ratio, which many of you probably saw. Again, the nice thing is I can cancel out the units I don't want, and I'm left with the only unit, mole, and substance that the question was asking for. And mathematically, it shows that I don't have to do anything. It's a 1-to-1 ratio. Times 1 divided by 1 gives me 2.25 moles. It would make sense that it's a 1-to-1 ratio. But the other product, starting with the same initial thing, 2.25 moles of NH4NO3, I want to get rid of moles of NH4NO3 and get to moles of my second product. In this case, it's water. Whenever I have a mole-to-mole ratio, this is a new thing, switching substances, I look to the coefficients. Again, in front of ammonium nitrate is a 1. Here it is again. In front of H2O is a 2. And if I double that, I get 4.5 moles of H2O. So that would be for each individual question will look like this. Oops. And you get a different amount of moles of each one.